Hey everyone, welcome back to Chem Story. In today's lesson, we're talking about something simple but super important, valence electrons. These outermost electrons are the ones that do all the work when it comes to bonding and chemical reactions. So let's break it down and learn what they are, how to find them, and why they matter. First off, what exactly are valence electrons? They're the electrons found in the outermost shell of an atom, and they're the ones that participate in chemical reactions and form bonds with other atoms. Valence electrons also play a big role in determining the chemical properties of each element. Since they're located in the highest energy level, they're also the farthest from the nucleus, which makes them more likely to interact with other atoms. Let's take a look at the electron configurations of carbon, nitrogen, and oxygen. In each case, the two electrons in the 1s orbital are called core electrons. That's because they're in the inner shell and don't take part in chemical reactions. On the other hand, the electrons in the 2s and 2p orbitals are part of the outermost shell. These are your valence electrons, and they're the ones that can form bonds or jump into reactions. They're at the front line of chemical behavior. Now, here's something we need to clear up: the difference between outermost electrons and valence electrons. In most cases, they're the same thing, but depending on how strictly we define valence, there can be a difference. Take the noble gases, the group 18 elements, for example. They have 8 electrons in their outermost shell, but since they don't usually react, some sources say their valence electrons are 0. So technically, even though they have electrons in the outer shell, those electrons don't participate in bonding, which is what the term valence is really about. That said, noble gases don't show up much in organic chemistry. So in most cases, especially in this course, we'll treat outermost electrons and valence electrons as the same thing. Now, if you take a look at the periodic table, you'll notice something really helpful. The number of valence electrons is closely related to the group number. If you look more closely, you'll see that for most main group elements, especially in periods 1 through 4, the number of valence electrons matches the group number. If the periodic table uses group numbers from 13 to 18, you can just take the last digit to find the number of valence electrons. So for example, group 15 elements have 5 valence electrons, and group 16 elements have 6. It's a quick and easy trick for figuring them out. Now, things get a little tricky when we start looking at transition metals. In these elements, the number of valence electrons doesn't always match the group number. That's because some of the electrons that take part in bonding aren't just in the outermost shell, they can also come from inner orbitals, like the d orbitals. So, how do we figure out the number of valence electrons for transition metals, especially in period 4 and beyond? Here's the approach. Start with the full electron configuration of the element. Then, subtract out the electrons that belong to the noble gas core from the previous period. If the d orbitals are completely filled, we usually don't count those either. So what's left? The electrons that aren't part of the noble gas core and aren't in a filled d subshell, those are considered the valence electrons. That's why, in transition metals, valence electrons aren't always just the ones in the outermost shell. They can include partially filled d electrons too. And this explains a lot, like why transition metals have multiple oxidation states and show such a wide variety of bonding behavior. Now, let's put this into practice with a real example. Take a look at nickel, copper, and zinc. They're right next to each other on the periodic table, but when it comes to valence electrons, the number doesn't just change, it takes a sharp turn. Let's start with nickel, which has an atomic number of 28. That means it has 28 total electrons. Subtracting the 18 electrons from argon leaves us with 10 valence electrons. These include the 2 electrons in the 4s orbital, plus 8 electrons in the 3d orbital, and because the 3d subshell isn't completely filled, those d electrons can still participate in bonding. So in this case, we count all 10 as valence electrons. Now move one step to the right, to copper, with atomic number 29. At first glance, you might expect it to have even more valence electrons, but it actually drops to just 1. Why? Because copper has a fully filled 3d orbital, 10 electrons, and only 1 electron left in the 4s orbital. Once that d subshell is full, it tends to act more like a core orbital, so we only count the 4s electron. That's why copper is considered to have 1 valence electron. Then comes zinc, atomic number 30. It has a full 3d orbital and a full 4s orbital, so it ends up with 2 valence electrons, both from the 4s. So just between these 3 elements, nickel, copper, and zinc, the number of valence electrons goes from 10 to 1 to 2. That's a pretty dramatic shift, and it all comes down to how the d orbitals are being filled and counted. All right, that wraps up our deep dive into valence electrons. We talked about what they are, how to find them, and why they matter, especially in transition metals. Understanding valence electrons helps you make sense of reactivity, bonding, and even oxidation states. Thanks for watching, and I'll see you next time on Chem Story.